Okay, so thank you again. And I want to thank the organizing committee for allowing me to talk about my research and tie this into the culture of engineering. I think some of you will find this work interesting because it has significant roots to the work I did at Penn State. So a lot of the work I do right now revolves around magnetometers, which help to determine what measure magnetic fields. And I'm going to be tying this in with the theme of the conference, culture of engineering, and describing how multidisciplinary teams are necessary and global efforts are necessary to accomplish such work. So real quickly, my current research involves three specific instruments. One's a time-result Raman spectrometer. My postdoc advisor, Jordana Blacksburg, is the principal investigator of this work. But this work is basically intended to identify minerals on other planets, such as Mars. There's going to be a Raman spectrometer being sent up in 2020. It's going to be similar to it's going to be put on a Mars rover, similar to the one on Mars right now, the Mars Curiosity rover, as you can see down here. In the bottom figure, this particular instrument is a LIBS, a laser ion induced breakdown spectroscopy laser. And the techniques are different, but they both involve lasers to shoot rocks and minerals. You look at received photons, and you're able to determine what specific mineral or even organics are on the surface. So that's one part of my current research. The other one is a gas and spectrometer radar. This one is basically an instrument, an orbiter that flies into the plumes of a planet or the dust and ice trails of comets. And so I'm doing a lot of the algorithm development work for this particular radar. The work that I am most excited about is this silicon carbide-based magnetometer work, and this is the work that I mentioned that I had significant roots to the work I did at Penn State. So this presentation, so I feel that the culture of engineering is heavily shaped by scientific discovery, especially at the Jet Propulsion Laboratory. And the reason I feel like this is because groundbreaking discoveries are made there every day. And this is only accomplished through advances in engineering. JPL technology is constantly being pushed, and one of their ultimate goals is to find life beyond Earth. And that, for me, is just a motivator to help me push the current limits of magnetometry. So many people may know that magnetometers help measure magnetic fields, but many people don't know that they are essential for finding water on remote planets. And I'll kind of briefly explain how this is done. But NASA always says, in order to find the life, you must find the water. So these magnetometers are perfect for reconnaissance missions in which we know not much about planets. So this presentation will illustrate the capabilities of the current magnetometers, how they've evolved over time for space research, and basically how the research that I'm doing right now ties in with the culture of engineering and how this involves magnetometer work. So real quick, I'm going to provide a brief overview of JPL. JPL is located in Southern California, and it's with the green star, as you can see down there. There's 10 other centers. But JPL is different from most NASA centers because it's run by the California Institute of Technology. So I'm not actually a civil servant or employee of the government. I'm a Caltech employee. But anyway, as you can see, JPL is located about 25 miles from the Pacific Ocean. There's Santa Monica down there on the coast. And despite being located only 10 miles from downtown LA, it doesn't feel like you're in an urban environment. As you can see from these next two slides, there's a lot of wildlife around there. Deer walking around all the time. You can walk up to them. You can't pet them, but they're close enough that you can pet them. I see people feeding them all the time. Lizards, and also we're right up against the mountains, so we get these warnings once in a while. Mountain lion have been seen on the mesa. Bear sighted have been seen up right up along the mountain there. And just recently there was a carcass found, deer carcass, and we think that was attributed to one of these mountain lions. But being in LA, I'm from Pennsylvania, so I love it here. I miss the change in season, so I miss the rain, which is surprising to a lot. But people in Southern California hate the rain, so this is just one slide. This is my, anytime it rains in Southern California, on my way to work, I see this on my phone. So this is what happens when it rains in California. This is just a Google snapshot of my phone. Accidents everywhere. It adds about 2 hours to your commute, so it's that's the one downfall about LA. So what JPL does, they are responsible for the deep space exploration of planetary systems, and they mainly do this with robotic missions. All the way from Explorer in 1958, the year after Sputnik was launched, to the Voyager missions, all the way down to the Galileo missions and the Cassini missions, and also the robotic missions of Curiosity. So I've got to see some, to meet some cool people and see some cool things. Over here, Disney's a big partner with JPL. They do a lot of collaboration. My wife actually works for Disney, so they bring their robots to our JPL to meet our robots. So up at the top we have R2D2, and at the bottom there's, I think it's BB-8. I haven't seen it in the movie, but you can see RoboSimian, our Scorpion robot made for the DARPA challenge in the background. The bottom here is the replica of the Curiosity rover. It's in the Mars Yard, and this is the rover they use to experiment with to send before they upload new firmware to the rover on Mars. Up at the top, Bill Nye the Science Guy. Met him a couple times now. Really nice guy to talk to. Morgan Freeman's come to give a talk. Obviously, Matt Damon from The Martian, he's come. This figure over here is the, unfortunately it's a bad picture. It's the only picture I have with him, but it's the director of JPL, Charles Alachi. So I just insert his photo there because of the bad picture, but just evidence that I do have my photo with him. And then the guy in the middle, I don't know if anybody know him, but he's one of my idols from when I was little. It's the Jizza from the Wu-Tang Clan. And it was quite interesting to hear his talk because he's a rapper from the Wu-Tang Clan, and a lot of his lyrics are inspired by science and technology. So NASA invited him out to give a talk, and it was actually kind of nice to talk to him about this. Okay, so real quick, I'm going to talk about magnetometry. So as you probably know now, magnetometers are essential for measuring magnetic fields. And there's two ways you can generate a magnetic field. One is by moving charge. So if you move current through a wire, as you can see up here, do we have a PowerPoint?
There's a
perfect.
that will change the slides and the laser pointers at the top.
Yeah, thank you. Okay, so as you can see here, if you pass a current through this wire, you have moving charge. So essentially, you generate a magnetic field. Similarly, you see these coils in a lot of magnetometer designs, and the construction basically says that if you integrate the current components, the field components into the currents in all of these, in this section of wire, you can generate nice uniform fields that look like this. And this is very essential for the magnetometer work I'm doing. So that's one. Moving charge generates a magnetic field. The other one is due to intrinsic angular momentum due to subatomic particles due to spin. So you have your elementary particles, the electron and the quark, and both of these are spin 1/2 particles, so they have a spin up and a spin down orientation. So these particles have a magnetic field, just intrinsic to their nature. And then you have the composite particles, the proton and neutron. Proton has 3 quarks, and because these they're fermions, they tend to pair, and when they pair, their angular momentum cancels. But because it has 3, it has a leftover quark, which means it's got a net angular momentum. So these composite particles, the proton and neutron, also act as tiny dipole magnets. Moving to the next level, at the atom level, protons and neutrons pair in the nucleus, and depending upon their configuration, if you have an odd number of protons or neutrons, the nucleus also can be magnetic. So as a result, you can do nuclear magnetic resonance. You've all heard of MRI. This is how MRI is done. And then also, the classical picture, you have an electron orbiting around the nucleus. These electrons are magnetic, but because an electron has charge, it's moving, it's another source of a magnetic field. So there's a lot of magnetic fields involved at the subatomic level that actually contribute to how a material is magnetic. We can all think of these as dipoles. So a lot of these things are important to the design of the magnetometer work I'm doing. So what are the applications of magnetic field sensing on Earth? A lot of you have seen and know much about these. Navigation, archaeology, magnetic resonance imaging, mineral detection, shipwreck detection, Submarine monitoring. Submarine monitoring is actually where the technology advanced, the fluxgate technology, and I'll explain that in a little bit. Magnetoencephalography, measuring tiny magnetic fields due to the induced currents in the brain. And then we all have seen this guy at the beach, this treasure hunting guy. It's a good source of finding treasure on the beach. So there's definitely a need for magnetic sensors in space, all the way from heliophysics to earth science and all the way to planetary science. So real quick, heliophysics. The sun's got its own internal magnetic field, and they call this a solar dynamo. So it's kind of a complicated process. It's due to gravity, convection mechanisms within the sun, and also kind of the rotation of the planet or the sun. But what you need to know is just what I told you earlier. It's moving charge. Within the sun are ionized particles that are continually flowing, and you have this flow of these ions. Essentially, it just generates a dipole field, and so it's electromagnet. So the sun's got a magnetic field, and all these other characteristics, these solar prominences, solar flares, these things, because they're ions, are coupled to the magnetic field because of the Lorentz force that you learned about in your physics classes. And also the interplanetary magnetic field sent out by the sun, its interaction with the Earth and other planets is very important to scientists. Earth science. Earth also got a dynamo effect. It's got although it's different from the sun because it's theorized that the internal structure of the Earth is an iron or nickel core with a flow of electrons or a flow of ions around that core. Essentially, get another dipole effect. And the Earth's field is actually relatively strong. But also the solar wind interaction and the aurora borealis all have effects to magnetic fields. And then finally, in planetary science, not all the planets have magnetic fields. Mercury has an active dynamo, and I actually want to point out real quick one of the, I guess, Michael Paul. Is he here? He's talking after me. There he is. I guess I just recently found that you were involved in the messenger mission. So, yeah, magnetometer on this particular spacecraft investigated Mercury, got some good data. Venus does not have a magnetic field. Mars does, Earth does. Mars has an extinct dynamo, so it's only got a crustal field, which can be measured, but it has to be measured very sensitively. Jupiter's got the largest magnetic field because it's a large planet. It's got a lot of internal mechanisms working within it. Saturn and Uranus and Neptune also have magnetic fields. And then we've also seen in the media this new planet 9. And it's probably not going to come into vision anytime soon, but Caltech definitely thinks there's one there. And I'd like to point out, too, that the Cassini mission with magnetometers on it claims that there was a report out there that due to the orbital perturbations that were felt, also predicted that the planet 9 was there, but that's not true. But anyway, other fields of other applications of magnetometry, crustal magnetic fields, like I said, on Mars and the Moon, on comets as well. There was a magnetometer on Philae on the lander of the Rosetta mission, but a magnetic field wasn't detected. But that doesn't mean there's a magnetic field or crustal magnetic fields on the rest of the comets. And then one of my, like I mentioned earlier, the driving factor for me is the search for life. Two missions specifically had magnetometers on board that helped find water on other planets. And this was the Galileo mission to the Europa and Jupiter. This guy down here. Essentially, the Galileo mission measured data which allowed computer models to predict planetary scale conductive liquid ocean underneath the ice surface of Europa. The Cassini mission to Saturn and Enceladus. There's been images of plumes, outgassing material in the southern plume of Enceladus. What Cassini was able to do was fly through these plumes, measure the ejected ionized gas, and measure the cyclotron frequencies of these ionized particles in the presence of Saturn's magnetic field, and the data was consistent with ionized water vapor. So because of this, we're going back to both of these planets. So first, Juno is going to arrive in 2016, or in Jupiter around, I think, July or something like that. here's it being fabricated. And in the Europa mission, this mission has actually been fully funded now, and the work continues to be going through NASA at JPL. And some of the magnetometer work that's going to be involved in this is to determine the characteristics of its ice sheet. And it's kind of troubling too, because they now want us to send a lander on Europa, and we know nothing about this planet, so it's kind of scary because it's a lot of work involved. But anyway, I want to point this out real quick. The magnetic field of the Jovian environment is very complicated, not only due to the planet, the moon, but there's also the solar wind, and there's also a lot of induced magnetic fields in a lot of these planets and moons. So I just want to play a quick simulation right here. Somebody did this at JPL. And this just shows you how complicated things can get. So this is Jupiter, right in the middle. And as I showed before, it's got an internal magnetic field, so you can see these are the magnetic field lines that it generates. Because its axis is tilted, its magnetic pole axis is tilted than its rotation axis. Here's Europa out here. The field that this guy sees as it orbits Jupiter is different at every instance in time. And because of this, you have oscillating magnetic field. This generates currents within the planet, which in turn generates another magnetic field. So it's an induced magnetic field effect. So it is very complicated. And the only way to predict this system, or to model this system, is with mathematical modeling. So it's very hard, because the magnetometer, all you get is one data point. And to be able to use that is very difficult. So you need very complicated models to determine what's going on here. Okay, so real quick, I'm going to go over some of the brief magnetometer technology that's used in space. The two main ones are flux gate magnetometers and optically pumped helium magnetometers. Flux gates are basically, they drive a ferromagnetic core, they sense an induced field, and then they use another set of coils to cancel that field. So these things are kind of bulky, so there's a limitation on how small you can make these magnetometers. But they're really reliable, and they're simple, and that's why they're flown on a lot of missions. Some of the missions they were flown on the Mariner missions to Mars and Venus, Pioneer 11, the Jupiter, Saturn, and interstellar space, the Voyager missions, Mars Global Surveyor, point out again the Messenger mission, Juno, and then Maven, which is flying around Mars right now. And these are just a couple pictures of flux gate. This is one taken of NASA, the Maven mission. And this is the Bepi Colombo for Mercury. This is the ESA mission. I'm not going to talk about flux gate operations, but I want to distract from the main point of the topic. Optically pumped helium gas. This is the next magnetometer used for increased sensitivity and stability. And this comes at the cost of using lasers and RF excitation circuitry. So here's a particular magnetometer for the JPL Pioneer missions. And here's one for the Cassini. And these were flown on the Mariner missions, Pioneer 10, Pioneer 11, Ulysses, the Cassini-Huygens Swarm, and Europa, which is being, which was the slides I just showed you. Once again, I'm not going to talk about these magnetometers because it's quite involved, but it's highly involved, related to the work I did in grad school, electron paramagnetic resonance and optical pumping tubes. Okay, so real quick, I'm going to talk about my own technology and how tie this into how this relates into the culture of engineering. So flux gates and optically pumped helium gas magnetometers are used mostly on space missions because of their proven performance, reliability, and their ability to adhere to the levying constraints of space missions. Additionally, all of the planets and a few of the moons have mostly been characterized. So why is there a need to continually develop magnetometer technology? Well, one reason is because the semiconductor technology field is rapidly improving. There's a desire to miniaturize, simplify the design, make purely electrical, and push the limits of sensitivity. And there will always be new missions, so we might as well use updated technology. Magnetic fields are everywhere in space, and they influence many phenomena like planetary dynamos, crustal fields, and the solar wind. And we don't have the complete picture. These things change over time. So it's necessary to get as much information so we can build up these models to better understand the planets and the evolution of the solar system, actually. As you can see here, are the two magnetometers I showed before, the flux gate and the optical pump. They're very good for these large missions where you can see here's to scale, there's a person working on these things. So these things are quite large, but there's a trend to downscale the technology to CubeSats. So these magnetometers don't fit really well on me here. So the next step is to look at semiconductor technology for this particular application. So this new proposed technology I want to introduce is basically you're detecting magnetic fields with defective microelectronics. You're actually using the defects within the microelectronic to sense the magnetic field. This can be done on a diode, bipolar junction transistor, or any kind of MOSFET. And I use a 4H silicon carbide MOSFET. And the reason I use 4H silicon carbide is because it's a really robust semiconductor. I had a great slide to compare this material system to Superman. But because of a lot of images I showed were taken directly from screenshots of the movie, JPL didn't allow me to show it. But I'm going to explain this anyway because it's actually a great analogy. Superman is the man of steel. Silicon carbide is stronger than steel. Superman gets his energy from solar radiation. You see him in the movies. He goes up the clouds, basks in the sun, and then he's all energized. Well, the same radiation gives these silicon carbide diodes essentially magnetic field sensing capabilities. It creates defects within the silicon carbide, so essentially makes it magnetically, it can read the magnetic fields after these defects are created. Thirdly, Superman has X-ray vision. Silicon carbide's got a band gap wide enough to measure X-rays. And then fourthly, the best one, I don't know, I forget what it was. I think it was the Superman 2 or 3. It was the one where he gets all pissed off for some reason, goes into a bar and starts flicking shot glasses at the back of the thing. I don't know if any of you remember that, but it shows that Superman cannot always be as sensitive and stable. And this is exactly where my technology is right now. It's not so sensitive and it's not so stable. Two of the best components that I need for magnetometry to show that this is good for space application. So it's unfortunate I couldn't show that, but that's essentially the gist of the silicon carbide material system. Some of the other advantages of my technology, here's just some particular components of the, parameters of these particular magnetometers compared to mine down here. And I call mine silicon carbide magnetometer, so just SIGMAG for short. So it's a good acronym. NASA likes the acronym, which is good. Compared to the sensitivity and stability here, right now I'm not at these numbers right here, tens of picotesla per square root hertz. Right now I'm about 400 nanotesla per square root hertz. And the units there aren't so significant. The lower the better is all you need to know. But eventually I think I can generate these numbers which is comparable with both of these technologies. So like I said, I won't talk about the physics, but essentially you have a diode, a silicon carbide diode, and you have the unpaired electrons associated with the defects. They're sensing magnetic fields. Electrons themselves are magnetic, like I showed. So when they're unpaired, they essentially have, they respond really well to magnetic fields and the current going through the device. Which is nice. What's nice that you can actually sweep a magnetic field across this diode, and you see a response that kind of looks like this. You can use magnetic resonance to excite a response off of zero magnetic field, but then you have this zero magnetoresistance effect due to the same mechanism. So it's a really simple device. All you have to do is sweep a magnetic field, and you can see this nice response. And this is particularly the signal that I'm using to detect magnetic fields. It's a little more complicated than that. Here's the complete picture. I use magnetic field modulation, so it's there's a lot of signal processing and actually communication systems involved because I perturb each axis with different frequencies, so it's kind of like a user channel. And I can measure the different components, X, Y, and Z axis. I can measure the magnetic field components of all axes using this Helmholtz coil design right here. This is just a generalized block diagram. I'm not going to go into it, but it's just there for completeness. So right now, I said the estimated sensitivity is about 200 nanotesla per square root hertz. And this is a theoretical graph of where I think I can get. So right now, here's the log of the sensitivity, and here is the essentially the delta I, or the change in current as a function of magnetic field. So right now I'm way up here, but I'm using a device that's like essentially off-the-shelf device. And the devices I'm using, they're intended for power electronics and not magnetometry. So it's just a coincidence that actually I was in Professor Lenahan's lab and we were able to find this effect. And this is in everything. So not only silicon carbide is good, a lot of other materials seem to work well too. Like I mentioned, silicon carbide is great because it's essentially rad hard, so it's great for space environment. So this is where I am right now. I have a nice intern building really pretty coils for me right now. So it's really tiny. And I can actually make this even smaller. This is just like a prototype. But right now, I'm at 440 nanotesla per square root hertz range. So at JPL, we have really nice fancy mechanisms or facilities to generate magnetic fields and be able to test these kind of magnetometers out. So here is I spend a 15,000 or 1,500 nanotesla square wave at different axes at different instances of time of my magnetometer. And these are the demodulated components that I see. And effectively, I can see this, which is a great sign. So I'm on a good path. And NASA thinks so too, because they just awarded me about $1 million for the next 3 years to continue to develop this technology. So I'm quite excited about this. And applications and future work. There's planetary entry probes, landers, missions in extreme environments, swarms of spacecraft significantly smaller than current nanosats. And then some of the future work, I'm going to be obtaining devices from NASA Glenn, who specializes in the fabrication of silicon carbide. Also, we're going to determine what processing specifications result with the best performing device. We're also going to work with the group to optimize the geometry and processing of these devices. And the next step is obviously to miniaturize and make it into a complete package, as you can see here. So, like I mentioned before, magnetometers require the effort of many. It's a multidisciplined effort. So you have the sensor design, which encompasses device physics, fabrication, and reliability. There's a lot of reliability issues in space. That's something that I actually need help with the people at JPO. Analog circuit design. You need to amplify very tiny DC or AC currents on the order of picoamps, which is very tiny. Also, there's mechanical design with coils, or even MEMS sensors, signal processing and communication systems involved, and then system engineering, of course, too, at the component level and at the spacecraft integration level. Data analysis and mathematical modeling, and computer science. So the measurements are useless if no one can make a model of these planetary systems. It's actually really nice to see that the computer science was merged with EE. Because this is something that is totally across discipline here in magnetometry. So both fields are definitely needed to develop this magnetometer. And then also the business sector, finance, public outreach, administration, all these things go into making these magnetometers successful. And then there's also a global effort. Just in the U.S., NASA requires the support from the public as is taxpayer funded. In 2016, the $4.1 trillion total spending budget, only less than 1%